everyone, and welcome to this introductory/review lecture I have prepared on descriptive statistics for the students enrolled in my research method course at UC Irvine. So descriptive statistics refer to an area or sub-branch of statistics that is specifically concerned with describing and summarizing the data that we have collected for a study. So we are not going to extrapolate any big level conclusions from the data we have collected. We are simply dealing at the level of how do I best summarize it so that I don't have to look at each individual data point, but instead try to extrapolate relevant summaries that tell me all that is to tell about the data I collected. So for this lecture, we're going to focus on three main tools. We're going to start by talking about frequency distributions, which provide a summary of how often or how frequently a given value in a variable is observed. So frequency distributions are going to be composed mainly of two bits of information. So first, we're going to have to identify what are the values that we observed for a variable. And here we're going to make an important distinction. If we're talking about a categorical variable, then we're going to be considering these distinct values as the distinctive categories of responses that we find. But if we deal with numerical variables, we are instead going to define mutually exclusive ranges of values, which we're going to be referring to as bins, across which we're going to be adding together the observations. Meaning that if I want to report the frequency distribution for my categorical variable final grade, I'm simply going to count the number of times each individual letter grade is observed. But if instead I want to report, for example, the frequency distribution on the hours of sleep that my participants have reported, well, it's going to be very impractical to report each individual different value that I find. Instead, I might construct meaningful ranges of values and then just clamp together all the values that appear within each particular range or bin, which is going to be the word we're going to be using all throughout this lecture. The second bit of information we require here is precisely the frequency count, which is going to provide information about how often or how frequently we observe values that fall within each unique category or range of values. So there are three main ways in which we can report this frequency. So the two main ones which apply for any kind of variable are the absolute frequency and the relative frequency. So the absolute frequency, as the name suggests, implies simply reporting the total number of times we observe values within a given category or range, just a number that reflects the total number of times that value is observed. Alternatively, we can try to contextualize this information by reporting the relative frequency, which is going to report the exact same information, but instead we're going to express it as a proportion, meaning relative to the total number of observations we might have. So instead of reporting just the total number of counts we have, we are now saying something about, well, what percentage of the total number of observations we had in total across all my categories does that particular category appear. A third type of frequency type that is going to be unique for variables that follow a natural order are going to be known as cumulative frequencies. So cumulative frequencies, as the name suggests, report the accumulated frequency, either absolute or relative, meaning either in terms of total counts or in terms of an accumulated proportion, up to a given category or particular value. And again, this up to is only possible because we're working with variables that have a natural order. How do we describe or communicate these frequency distributions? Well, there are two general approaches. Typically, if we have a few categories or ranges of values, then we are better positioned to use the frequency table. But if we have a lot of categories or frequency, or bins, we might better work with a frequency distribution plot. Why is that? Because it's going to be much more practical to read than to peruse a table with many categories and lots of information for each of those categories. So here we have a nice little example of a frequency table. We are focusing here on the categorical variable letter grades that we had on the table on the very first slide. So in here we can see that we can either report the absolute frequency by simply counting how many times each of these letter grades is observed and reporting that, or we can also transform and communicate this exact information in relative terms. So this example works nicely just because we had exactly 100 observations. So the only thing we're doing, and it's very transparent here, is converting these absolute counts in percentages or in proportion terms, such that we can say something about, well, yes, I observed 23 participants or students that had a letter grade A, but how much is that related to the total number of observations we had? So we can now say that 23% of the students got a letter grade of A. The values are just very similar because, again, we just had 100 students in our sample. And this is, of course, all made up data. Then we can also report these values in terms of a cumulative frequency that can either be expressed in terms of the absolute count or the relative frequency. So in here, the only thing we're doing is we're taking advantage of the fact that these letters have some sort of order. So we know that an A letter grade is in general indicative of a better performance than a B letter grade, which is on itself indicative of a better performance than a C letter grade, and so forth. So we can take advantage of the fact that these categories follow a direction, have an order, to report the cumulative frequency. So in here what we're saying is we're taking one of the extremes as the start of our scale. So in this case we're going to start with A. This is totally arbitrary. We report the total number of observations we have there, so the absolute frequency and the relative frequency stay the same. And then when we move to the next category, because again we know there's a progression, what we're going to do is we're going to add the counts, the absolute count or the relative information that was added by this following category. So now we have 55, which is 23 plus 32, 0.55, which is just converted to percentages divided by 100. And now I can say something about the total number of people that got a letter B or greater in the, I don't know, whatever this is corresponding in the last quarter, in the last exam, in whatever you want this to represent, was 55. And then I can continue doing that. Now I want to also consider the people that got a letter grade of C. So again, I can just add that together with the previous counts and the previous relative frequencies to say something like, well, I know that in this class, 77 people, or 77% of those students, got a letter grade C or higher. So I am now reporting all these values, which are relevant because they are ordered together in a cumulative way. And just in case you were wondering, so this right here is just an arbitrary way of presenting this information. I have here chosen to represent the different values across different rows and the different types of frequencies on different columns. But I could have the exact same information portrayed in a table that looks like this, where now I have the distinctive values on the different columns and the different types of frequencies allocated across different rows. The second tool we might have when trying to communicate the frequency distribution of a variable, which is going to be even more useful when we have more categories or more ranges of values to report, are frequency distribution plots. Let's start by talking about the specific distribution plots that we can use for categorical variables. And here we have two very basic types of plots that I'm sure you have encountered before. I have here a general description of them, but I find more useful to talk about them if we're looking at an example. So here we have a bar plot. A bar plot is a type of plot that has this name because each individual bar represents a different category. They might follow an order, like it is the case here, so we know A, B, C, D are letter grades that follow a general order. We know that an A is greater than a B and so forth, and vice versa. We know that a D denotes a lower grade than a C and so forth. But what's important here is that there's going to be this spacing here to indicate that we do not necessarily assume that they are moving within a numerical continuum. So these are just counts of distinctive categories. And the height of each bar is going to tell us something about the frequency with which that particular category of response or categorical value was found. And now, what exact information we present on the y-axis is going to be up to you. What do I mean by that? Well, we can really use the y-axis to display the absolute frequency, so the absolute count or the total number of times each particular category is observed. Or we can use the y-axis to denote the relative frequency. So we would instead be portraying here information about the proportion of times that each particular category was found. And of course, these two types of plots are always going to have a very similar shape because again, the proportion is nothing but a transformation of the absolute counts that we encounter here. Next, we have here cumulative frequency. So it is entirely possible to build a bar plot that on the y-axis displays either in absolute terms or in relative terms the accumulated count of the instances that we find values up to a given category. So again, we are working with letter grades, which we said is an ordinal variable. And notice here that I have flipped the order with respect to the frequency table. So in the frequency table, I had arranged this kind of like in a descending order. So we started with A and went back to D, and we kind of took that order into account when building the cumulative frequencies. So we were saying things like 55% of people got a B or larger. That is something we can do. In this case, I have instead arranged my letter grade variable in an ascending order such that now when I report the cumulative frequency, I'm going to say instead, well, this right here is the number of people that got a letter grade of C or lower, because I have added now the number of observations that I had with a letter grade D plus the number of observations that I had with a letter grade C. And we can verify that because here, where we report the category-specific absolute frequencies, we see that both C and D were found for something close to 20, 21, 22 people. So if we add those numbers together, that's how we get this for here. And then we move to the next category, and now we add this total or accumulated frequency to the number of people that got a letter grade of B, which seemed to be a little bit more popular in this class. And now we get that value reflected here. So again, the point of this slide is just to say the underlying data, so all of these slides are built in this fictional data set that I have provided, but they communicate a different aspect of that data. And that is really the core of this lecture today. So descriptive statistics are going to be about how and what we decide to communicate about our data so that we can tell a summary of it. Now, the second type of categorical frequency plot that we're going to be discussing is the pie chart. So the pie chart is very enticing. The pie chart looks like this, has the name because it looks like a pie cut in pieces. So we're going to have this general circle, which is going to be divided on slices, one slice per categorical value observed. And then the area of that particular slice is going to represent the relative frequency of that category. So unlike bar plots that can be used to represent any kind of frequency, pie charts are only going to be used for relative frequencies. And pie charts are very enticing, are very tempting because they look very pretty, they are very colorful, they seem nice. But I want to address your attention to the fact that they are quite impractical and difficult to read. In other words, when I presented to you this bar plot here, you could immediately tell right away that the category that was most observed was B, but that in general there seem to be roughly the same number of people that got a letter grade of A, C, and D. You get the story of the data with just a glimpse. But if I present to you the pie chart, it takes a little bit of more staring to try to get an evaluation for whether the areas between these three categories are the same or not. Because at a first glance they look identical, but that is not the case. So we have here one that is a little lower. It's also difficult to evaluate how much bigger this category. So even though you can see at first glance that this green area here seems to be a little larger, it's difficult to judge quickly or at a first glance exactly how bigger it is than the others. So we see here that there is a difference of almost 10% between this category and any of the other areas. And that is quite difficult to judge at a first glance. Alrighty, and then we move to numerical variables. So when we work with numerical variables, the standard plot for visualizing frequency distribution is going to be the histogram. Again, a histogram is a plot that looks pretty much like a bar plot, except that this time each unique bar, instead of representing a categorical value, it's now going to represent a specific range of numerical values observed in my variable. And because this range of values are kind of arbitrary, so they can be defined however you want as long as they are mutually exclusive, the total number of bins or ranges that we define is going to have a strong impact on the resolution of the distribution. So how fine level detail are we able to extract from the plot. And lastly, we see that histograms are typically only used to display either absolute frequencies or densities. Now, densities is a word that it's an approximation to the relative frequency that is being adjusted for bandwidth. You don't have to worry too much about it. Just know that a density conveys the same information as a relative frequency, but we cannot expect it to add up to 1. The nice property of histograms is that by just looking at them, we're going to be able to extract information about, say, what is the general shape of the data distribution. We're going to be able to very quickly tell whether the distribution is symmetrical, is skewed. It's going to tell us right away which are the most common or the most extreme values that we observe. So here we have an example of a histogram for our numerical variable sleep time, so the number of hours that people reported sleeping. And again, just by looking at this histogram, takes us less than 3 seconds to immediately locate. So what are the values that are observed most frequently in this variable? What are the values observed? So we see that in general, most people seem to sleep around 8 hours. But we see that a few of them also tend to sleep more than 10. So jealous. But a few of them sleep less than 4. Maybe they were very stressed, had a busy week, whatever. The point stands that just by looking at this histogram, we get a quick, full story of the data. And again, it looks a lot like a bar plot, except that now, again, the little bars are going to be connected to capture the fact that they do now move along a very clearly defined continuum here, because we are plotting values that follow within the numeric line. Okay, so when working with descriptive statistics, we said that frequency distributions are one of the very first things that we can report to try to provide a general summary of what our data looks like. The next thing we're going to be able to do is compute summary statistics. So summary statistics are going to be numerical quantities that are going to allow us to describe and communicate or summarize some important feature of the data that we have collected for a given variable. So one example of a summary statistic that you are already well familiar with, regardless of whether or not you have been referring to it as a summary statistic, is the mean. And why is that? Because the mean allows us to quickly identify and communicate what is the center of the data that we have collected for a given variable. And let's take this opportunity to introduce some basic math notation that we're going to start using throughout the course. So we're going to be using the notation xi to refer to the ith value. So I is going to be here a little index. To refer to the ith value for the variable x in a collection of n observations. So n is going to represent the total number of data points that I have for a given variable. And then we're going to be using the bold letter x, which is mathematical notation for a vector, which is the collection of all individual values I have for my variable. So here I have my first value of variable x, my second value of variable x. I keep going until I get to the last value, n is the total number of observations. So this is the last observation that I have of my variable x. And from now on, we're going to be thinking about summary statistics as single quantities that I compute that summarize this whole set of observations that I have. There are three main types of summary statistics we're going to be covering today. The first ones refer to measures of central tendency, which provide information about the center or the typical value of the data. An example of this type of summary statistic would be the mean. Then we're going to have measures of dispersion, which, as the name suggests, are summary statistics that tells us something about the spread, the dispersion, or the variability within the data. So an example here is the standard deviation. And last, we're going to talk about measures of position, which are summary statistics that helps us identify what position does a given value take in our entire string of observations that we have collected. So a familiar example you might have here is the percentile, which I know was covered in one of the prerequisite courses. We're going to talk a little bit more about it in a second, just to make sure we're all on the same page. So measures of central tendency, we said, are summary statistics that describe the center or typical value of the data. The best known one, or the one that you're most likely familiar with, is the mean, which corresponds to the arithmetic average of all data points. And we have here a nice little math equation to remind ourselves of how it is computed. So the mean is always typically going to be represented by this x bar notation. So this is always going to refer to the arithmetic mean of some variable x in this case. And it's going to be computed by adding together all my observations. So I'm going to be substituting here my I-index with all numbers between 1 and n, where n is the total number of observations I have. This big symbol is a sum operator, so this is indicating that everything that gets fed into the sum, it's going to be added together. So we're going to add all individual observations, and then we're going to divide that total sum by n, which is exactly what you know the average is. It's just the sum of all individual observations divided by the total number of individual observations you have. Now, something to keep in mind when working with the mean is that the mean is going to be very sensitive to outliers, because we are simply adding values and dividing by the total number of values we have. So if in our data set the person that was inputting the values accidentally made an error, made a typo, and added one order of magnitude to an observation, maybe, I don't know, when recording the scores of participants in an exam, then that big number is going to dramatically increase this total sum. It's not going to really reduce the way it gets weighted down by the total count, because this is just a matter of how many observations we have. And then we're going to end up with a mean that is going to be heavily impacted by that one very large number. Then we're going to have the median. The median is going to be a summary statistic that helps us describe the middle value observed once we have ordered our observations. What does this mean? That I'm going to take my values from smallest to largest, and I'm going to try to locate what is the value that falls right at the center of that ordered list of values. Now, the neat property about the median is that the median is going to be robust to outliers, because even if I add a very large number or a very small number, well, those are going to be placed at the edges of the ordered list of data, and they're going to be discarded once I try to locate the value that falls at the center, or the middle value. And lastly, we're going to have the mode, which is a summary statistic that describes which is the value that is observed most frequently. And now the mode is the only summary statistic that we can and that makes sense to report for categorical variables. So typically all summary statistics, because they all represent some quantity that gets computed from the data, they all only work for numerical variables. The only summary statistic that can be computed for categorical data is going to be the mode, because it's just going to be a matter of locating what is the category that is observed most frequently. Now, you might think that you could report the median on ordinal categorical values because they have an order and you can arrange the two observations we have, but that doesn't really make a lot of sense because typically that middle value is just going to be the middle category. Because the data being ordered is just ordered in terms of categories that have very limited information. Reporting the median is not really going to be informative of anything. It's very likely going to return just the middle value, and then there's nothing really useful that we can communicate with that. Okay, so now we have an example of how to compute these measures of central tendency. I'm going to go through this very quickly. You can work on this on your own. So here we have some observations for a variable x, whatever you want this to mean. Maybe this can be scores in an exam, for example. So we can easily compute the mean of this vector of values by just computing the arithmetic average. So we just add them all together and divide them by the total number of observations. So we add them all, divide them, and get a mean of 86.9. We can then sort them from the smallest to the largest. So these are the exact same values, just sorted, and then find what is the value that falls at the middle to locate the median. And we can count how many times does each individual value appears to locate the mode. Then we have measures of dispersion, which again are summary statistics that describe the spread or the variability in the data. There are three summary statistics that we're going to be talking about today. The first one is the range, which is just capturing information about the difference between the maximum and the minimum values. Notice that the range as a summary statistic is a single value that results from subtracting the maximum value from the minimum value observed in our data. It's not going to be the minimum and the maximum, it's going to be the difference between them. Then we're going to have the variance, which is going to be the average square difference from the mean. So for each individual value that I have observed, so again I'm substituting this I index with all numbers from 1 to n, the total number of counts. For each individual value, I'm going to subtract the mean so that I know how different from the mean or how distant from the mean each individual value is. Then I'm going to square that difference to prevent the impact of this value being negative and positive and then canceling each other. So I'm going to ensure that they are always positive by squaring this difference. I'm going to add together those square differences across all my observations. And then I'm going to divide that by n minus 1. This minus 1 is a correction to ensure a better estimation of the variance in our data. Again, don't want to get into that, but that's the formula we're going to be using. And this variance of our data, it's typically going to be denoted with this notation. We're going to be using s squared to refer to the variance in our data. Then we're going to have the standard deviation, which is, again, using a similar notation, which is simply going to be denoted as the square root of the variance. So we have here the exact same formula. We are just squaring it to compute the standard deviation. Now, the third type of summary statistic we're going to be discussing today is going to be known as measures of position. So measures of position as a type of summary statistics allow us to identify what is the position that a given value takes after we have arranged or sorted all the data we have collected for a given variable. And we're going to specifically talk about quantiles as a type of cutoff point that divides that space. So we're going to arrange again our values observed from the smallest to the larger. And we're going to be using quantiles to divide that range of values, of ordered values, into equal parts. And how many equal parts we defined is going to define the specific type of quantile we're talking about. So there are two very well-known types of quantiles that I'm sure you had been exposed to before. So percentile are a type of quantile that split that space into 100 locations, such that each percentile, so the first percentile, the second percentile, third percentile, up to the 100 percentiles, allows us to identify what is the value below which a given percentage of the data falls. So if I think about the 30th percentile, I would be looking at whatever value in my data, 13% of the data falls below off. We're going to see that in an example in the next slide. The second type of quantile you might have heard about are the quartiles. So quart, as in a quarter, divide the space into 4 equal parts, and so each quartile is going to represent 1/4 of the data. So the first quartile is going to help us identify what is the value that splits the first 25% of the data. In other words, what is the value below which 25% of the data falls. And hopefully you have realized this, but because the percentile divides the space into 100 pieces so that we can say something about percentages, and the quartile divides the space into 4 equal pieces, the second quartile and the 15th percentile are going to mean the exact same thing, because the second quartile captures the first 2/4 of the data, so that's the same as the 50% of the data. They both indicate the median, because again, the median is going to be the summary statistic that captures the middle value, the value that follows right at the middle of my arranged vector of data. So let's take a look at how we can go about very quickly finding percentiles once we have ordered our data set. So in here we have fictional data. So the first row here doesn't really mean much, it's just conveying something about the position. I have ordered 15 observations from the smallest to the largest. So here are the distinctive values that we have here. I don't have 100 values here, so how can I go about describing percentiles in this case? Well, first what we're going to do is we're going to express the desired quantile as a proportion between 0 and 1. So let's say that we're interested in the 25th percentile, which we know is also the first quartile. So the 25th percentile, we're going to express it in terms of a proportion between 0 and 1. It's going to be equivalent to saying 0.25. The next thing we're going to do is we're going to multiply this proportion value by the total number of values we have observed. So we have 1, 2, 3, 4, 5, 15 total of observations here. So we're going to multiply this 0.25 times 15. The next thing we're going to do is we're going to round up that value to the next integer. This is going to be the position at which I have to look for the value that corresponds to that quantile. So for the 25th percentile, first I'm going to express it as a proportion, then I'm going to multiply that by the total number of observations I have. That results in 3.75. I round this to the next integer, so this is a 4, and this is now the position of the quantile. It's on the 4th position. So I go here, 1, 2, 3, 4. The value that corresponds to my 25th percentile is 22. So I can say that 22 is the value below which 25% of my data falls. And then I can try that with different quantile values. So I will leave this to you, but it's the same logic. Alrighty, so now we're in a position where we're very well suited to talk about box plot. So box plots are a type of distribution plot that doesn't really use information about frequencies. It doesn't really care about how often a given value or values within a range fall, but it's going to still give us some information about the variability in the data that we have observed. So it's going to work only for numerical variables, and it's going to rely heavily on reporting quantiles. So this is what a box plot looks like. It has the name because it shows a nice little box, and it's going to be very special because the location of this box, it's going to convey information about the median of my data. The lower end of the box is going to correspond to the first quartile, so I know that this is the value below which 25% of my data falls. And the upper end of this box is going to tell me something about the third quartile. So this is the value below which 75% of my data falls. And then we're going to use whiskers to capture the spread of the data. And these nice little dots are going to be sometimes shown to capture outliers, values that fall outside this range defined within 1.5 times the interquartile range. So these are going to be kind of like a rule of thumb that box plots are going to use to classify an observation as an outlier. So here we have an example of a box plot constructed on the very same data that we had used to construct a histogram a couple of slides ago. Alrighty, so the last thing I wanted to talk about today is covariance. So covariance is going to serve as a measure of association between any two numerical variables x and y. So before this, we had been talking about descriptive statistics that can help us summarize the information we have collected across our many observations for one given variable at a time. And we had made a very explicit distinction between what to do when this variable is categorical, what to do when it's numerical. But right now we're going to be instead focusing at the association between two variables where both of these variables are numerical. And now I wanted to make a quick little clarification here because I have placed this topic at the end of our discussion on summary statistics. And depending on the text that you're checking, sometimes covariance is listed as a summary statistic, sometimes it isn't. That is not going to be relevant for us. I just want to draw a clear picture of what is the information that the covariance communicates. So the covariance, again, is going to focus on two variables at the same time, and it's going to provide information about whether or not the values that we find across these two variables seem to be moving together or in relation to each other or not at all. There is not a pattern or there is not an association between them. The covariance is going to be computed using the general equation that we have here. Now it looks a little convoluted, but it's very intuitive to read. For each particular observation that I have across my two variables, and of course this all is sustained on the idea that we have measured these two variables for the same objects, so maybe for the same participants we have information about x and y, but the idea is that these two observations have to be able to be paired. So here we have the index, so I1 is going to be the first subject, for example, so xi is going to be the measure for variable x, whatever it might be, that I have for subject 1, and then yi is going to be the observation that I have for variable y for the same person. So I'm trying to see whether across my observations there is a pattern or a relationship between these two variables. So the idea is that for each individual index that I have here, I'm going to look separately at the values of my variables x and y. I'm going to look at how they differ from the respective means. So maybe I'm looking at the observation I have for participant 1, and I want to see how they perform with relation to the average test score. Maybe x is a test score here. And so it could be the case here that this person performed above average, so this difference is going to be positive. And then I look at variable y, which might be the number of hours they sleep, for example. So I'm going to compute the difference between that person's number of hours per sleep and the average number of hours of sleep that everybody reports. So this is the average of that variable. And let's say that in here I find that again, this person slept more than average. So once again, this difference is going to be positive. I don't know what the values might be, but I know for sure that if I multiply a positive number by a positive number, I get a positive number. So I start by having that as my first value that I'm going to be adding together, right? Because we said that this symbol here denotes a sum. So then I move to my second participant, right? Because I is a subindex that moves from 1 to n, where n is the total number of observations I have on each variable. So I move to my second participant. And I do the same thing. I look at how their specific value of variable x differs from the mean of x, and how their specific or individual value of y differs from the mean of y. And then again, depending on whether this person is located at the same place with respect to the mean, so whether this is positive or a negative difference, and whether this is also a positive or negative difference, I'm gonna get some number that is either positive or negative, and it's going to get added together across my entire sample. So once I have done that for every participant or every observation that I collected across my two variables, I'm gonna again multiply that by this little fraction, so I'm gonna end up just dividing that by n minus 1. Again, a correction that we're not gonna be concerned with. So how do we interpret our covariance? So if we get a covariance value that is positive, that seems to denote that consistently it seems to be the case that the values that we find between or across our x and y variables are consistently either above or below their means. Why is that? Because for participants for which their individual observations of x and y are above the mean, these two differences return each a positive value, and positive times positive is positive. And for participants that fall consistently below each of these means, so have a lower value of x than the average of x and a lower value of y than the average of y, these differences each are going to return a negative value. So we have two negative differences here. If we multiply them together, negative times negative, it's going to be positive. So if we keep adding a bunch of positive values together, this whole covariance is very likely going to end up returning a positive value, right? Which indicates that both values seem to be moving in the same direction with respect to their own respective means. Now, if we get a negative covariance, we instead are talking about a case in which it seems to be that consistently, when one of the variables is above the mean, the other variable is below the mean. Because the only possible way in which this multiplication or this product here returns a negative value is if one of the differences is positive and the other is negative. And if I keep adding together negative number plus negative number plus negative number, I'm going to end up with a covariance that is negative. So this indicates an opposite relationship between my two variables. One increases, the other decreases. Now, if my covariance has a value that falls close to 0, that might indicate that there is not a systematic association. What does that mean? That in some cases this product might be negative, but in some other cases this product might be positive, and they end up canceling each other when we add them together and return a covariance value that is closer to 0. Now, there is something that hopefully you have picked up, and that has to do with the fact that the specific number that I find, it's going to depend heavily on the scale of the values that we find across our x and y variables. In other words, it might be difficult to judge how close to 0 do we have to be in order to assert that there is not a systematic association between our two variables. For the visual learners out there, here is another representation of how the covariance is computed. We have here variable x and variable y, each of which has their own scale of values. So in this case, I have arranged them to be centered around 0 just for simplicity. We have here on the margins the marginal distribution of each variable. So this histogram here just captures the distribution of values of x that we have. Here in red I have marked the mean value, so the average value of x. Here on this axis I have the marginal distribution of y values, so the marginal distribution of values of y that I have observed. And in red I have marked the mean, the average value of y. I have added these dotted red lines to cut down the joint space. So in the center I have a scatter plot for which each individual point here captures the pairing of values of x and y that I have observed for a given individual. So what I'm trying to represent here is the way that the covariance formula works. So the idea here is that for each individual data point, I'm going to be plugging that data point into this covariance formula. such that what I'm looking at is the placement of that value across the x and y spaces with respect to their own means. So in here I have a value that on the y-axis is below the mean, right? So it's below this value that I have here. So this would be a negative difference. And it's also below the mean of the x variable here. So here we have the mean of the x variable, and this value seems to fall below its mean, so this difference is also going to be negative. If I multiply negative by negative, this whole value is going to be positive. And then I keep doing that for any other dot that you might find here. So again, whether this covariance is positive just indicates that consistently across many observations, we find differences that move in the same direction with respect to their mean. When this covariance is negative, it would indicate that instead we had the opposite pattern, where as one variable increases, the other decreases. And a covariance of 0 would simply correspond to a case where we have most dots located across just a flat space. So there is not a concrete pattern where as one variable increases, the other also seems to increase or decrease along with it. But again, we are still left with the problem of the lack of a scale. So here we have 3 arbitrary examples here. So in here I have clearly a positive association between my 2 variables. So as one variable increases, the other increases as well. And when I compute the covariance, I find a positive value, just as expected. The specific value that I observed is 64.5. Now here we have a very clear negative association. As one variable increases, the other decreases. We compute the covariance. Again, as expected, we have a negative covariance here with a specific value of negative 65.4. But then here we have an illustrated example where there is not an association between my two variables. So hopefully visually you can see it here. There doesn't seem to be a trend. There is a very, very minor trend here, perhaps drawn by this line, but it doesn't seem to be very strong. However, if I compute the covariance, I end up with a positive value of 19.2. So how can I judge this value? What does this 19 mean? How close to 0 it is? So here enters the Pearson correlation coefficient, which we're gonna be denoting with this nice little letter R or the Greek letter rho. So the Pearson correlation coefficient is going to be heavily built on the same idea as the covariance. So in fact, you can see here on the numerator the same we had been using to calculate the covariance between any 2 variables x and y. But it's going to include this fancy looking denominator, which is just the product of the standard deviations of each variable. And what this denominator is going to ensure is it's going to help us ensure that this value of the covariance is now going to be standardized and restricted to live within a space between -1 and 1. So with this, the Pearson correlation coefficient provides a measure of the direction of the linear relationship between the 2 variables. This was obtained by using the covariance. But by having this standardization component here, it's also going to quantify the strength of that association. So a Pearson correlation coefficient value closer to either -1 or 1 would indicate a perfect association between my 2 variables. And then as we get closer to values near 0, we say that the association is weaker, or perhaps even that there is none at all. Now, there's one last thing I should say about using the Pearson correlation to quantify the association between any 2 numerical variables, and that is that it's only going to detect relationships that we describe to as linear relationships. They must be describable using a straight line in the sense that it should be a monotonic pattern. When one variable increases, the other increases, or when one variable increases, the other decreases. If the pattern is curved or non-linear, these products might cancel each other because they might no longer be consistent, and it might end up leading to a value of the Pearson correlation coefficient that is close to 0, even though a relationship clearly exists. So here we have an extreme example. This is made up data, obviously, where both variables seem to be clearly related. So there is a very clear pattern where the changes of x does lead to very consistent changes of y. But this relationship is no longer describable using a single straight line. Instead, we have here what we roughly refer to as an inverse U relationship. So there's this pattern where for low values of x, there seems to be a positive association, but for higher values of x, the relationship seems to change direction. The problem is going to be that if I try to plug in this data before plotting it and compute the Pearson correlation index, I might end up with a value that is very close to 0 that suggests a lack of association, simply because the trend that I observe here is going to cancel the values of the trend that I observe here when I try to compute the covariance. So in other words, I have half as much points that follow one direction and half as much points that follow the opposite direction. So now they are canceling each other and they are returning a value that is very close to 0. All right, and here is the question for you for today's lecture. So you are given this fictional vector of data. So there is, I think, 20 observations here. You have to compute some summary statistics and build a complete frequency table that shows all types of frequencies. Please do remember that because this is a numerical variable, we don't really report frequencies in terms of unique distinctive values that we find. Instead, what we do is we find meaningful ranges. Alrighty, so if you have any questions, please do send them to me in any possible way you can. I will try to get back at you as soon as I humanly can.